Good afternoon. My name is Travis Walter, and it is my pleasure to be introducing our work on personalized cancer therapy by unlocking the power of gene expression. The overall goal of this project is to use unique patient gene expression data to classify specific cancer types, ultimately identifying potential drug targets for SigmaFactor Pharmaceuticals' research team to pursue and develop drugs for. Our objectives will serve as the agenda for this presentation going forward. I will be introducing the problem that we're trying to solve. Chauvin next will discuss in more detail the business case we've laid out for this project. Suba and Dinesh will discuss the data sources that we used, the models that we developed and built, and the outcomes of these models. Carrie is going to demo our Tableau dashboard and mobile app for visualizations and self-service analytics. And in the end, I will wrap up the findings in all of our work. There is currently a revolution happening in the treatment of cancer. Personalized medicine would be a much preferred method to traditional chemotherapy. Chemotherapy drugs are generally extremely toxic, non-selective in the killing mechanisms, meaning they target both healthy tissue and cancerous tissue, and the side effects are extremely difficult to cope with. Precision medicine can leverage current steps in the path of treatment, namely biopsy and diagnosis. The difference is that we use state-of-the-art biology and sequencing technologies to get a fingerprint on the individual's unique cancer tumor to develop treatment and therapy. We believe personalized medicine is the future. This genetic information can provide better insights to doctors and clinicians. The two left figures show how heredity could play a role in drug response. This information would not be known if the sequences of the patients remain a mystery. It could be the case that people would be treated unnecessarily more than once without knowing this information, or would respond poorly to a drug regimen. The cartoon on the right tells a story on what the future could look like. Gathering the patient's genetic information first before deciding on a treatment plan to get the drugs and dosing right the first time around would be a preferred state. This is a very difficult problem to solve. But how would we approach the problem? We would approach it by applying advanced analytics and predictive modeling using patient data. This concept is not necessarily a new one. However, with the recent drop in DNA sequencing, as can be seen on the graph on the right, we can now collect data on significantly more patients than we ever could have imagined years before to make these modeling approaches possible and to get the sample sizes that are large enough to distinguish the signal from the noise. Our ultimate goals for this project are twofold. One, to decrease the cost of drug development and ultimately save money for SigmaFactor Pharmaceuticals research and development team. Two, to make treatment more cost effective. If we can get cost of treatment down low enough, SigmaFactor Pharmaceuticals will for sure be the preferred provider for cancer therapies moving forward. The remaining parts of this presentation will show how we plan to accomplish these goals. The first main objective is the business case, and Chauvin will be presenting on this next.
Thanks, Travis. I will take it over now and to explain the business case that we are building for SigmaFactor. So at SigmaFactor, we believe that the future of low-cost personalized cancer treatment is now. And we strongly believe in this cause, and we are out front to solve this problem head on. As we all know, that the market for cancer treatment is growing, evolving very fast, and is very demanding. Market is demanding that costs should go down so that it's easier for everybody to handle the cost of the cancer treatment. The cancer drug market is currently at all-time high, and it's growing really fast. The global market for cancer drug has hit 100 billion now, and it will reach around $150 billion by the end of 2018, and for the foreseeable future it will continue to grow. As we see in this graph, the growth of the cancer drug from 2009 to 2018, and it has been segregated by the main countries, main developed market. As we can see, In sky blue, the biggest market is US market, and that's where we are focusing our effort to be in. And as we can see, in 2018, the market would be $147.9 billion. As we all know, as everybody knows, either you are a patient or you are in medical profession, that the cost of cancer treatment is too high. Patients are suffering, insurance companies are suffering, employers are finding it hard to provide insurance to employees due to high cost. It's taking it's taking financial as well as emotional cost on the patient. Nobody talks about the emotional cost that a patient goes through when he or she diagnosed with cancer, but it's huge and it takes toll on everybody in the family too. Insurance companies are also suffering due to high cost of the providing cancer treatment. So what is our value proposition at SigmaFactor? SigmaFactor is looking to solve this critical problem with technology. We want to use data which is available in abundance these days, and try to build models with the low computing cost that has uh, come to fruition in last 2 3 years. So that's how we want to solve this problem. SigmaFactor is dedicated to solve this problem by using high volume of data availability and low cost of computing power. We'll keep our business model with operating cost low, so that we can compete with the big this pharmaceutical companies. And how we are trying to fix this problem or to solve this problem is through data and the low computing cost. More data has been produced in last 2 years than all of previous years combined, and we have availability of high quality of genetics data. That's what we found when we started building our model, and before that we started doing our data preparation. What we found that the data quality was really good. uh, Sigma Factory is focused on using high quality genetics data with low cost computing power to build the models, and these models will be used to come up with the personalized cancer treatment. And these personalized cancer treatment would be at low cost. One of the main value proposition of Sigma Factor is that we'll keep our operating model at a very low cost level so that we can compete with the big companies like Pfizer and the other companies. A low cost operating model will help Sigma Factor to compete with big companies and to deliver cancer treatment at a cheaper price. Sigma Factor will use low cost computing power in order to build the model, which will be used for personalized cancer treatment. Sigma Factor will use offshore model to keep the cost low, means we'll do all the mundane work, like all the mundane data work offshore, and that will help us to keep the cost low. So, what we believe at Sigma Factor is the time has come uh, to, uh, to, to tackle this problem head on, and we are taking the lead in providing low cost cancer treatment which is personalized. Like what we have seen, that one size fits all model has not worked in the past, so we have to come with something which is more personalized for every patient, so that is cost effective for that patient, that particular patient. um, Use of technology is not just one option, but it's the only option now we have to solve this critical problem. We have a solid business case with simple but effective business model to solve this problem. Now I hand it over to Suba, who will go over the data preparation part of the project. Thank you very much.
Thanks, Chauvin. I will be explaining the characteristics of the data, transformation, and exploratory data analysis that we performed. We have acquired the data from the UCI machine learning repository. The name of the dataset is Gene Expression Cancer RNA-seq dataset. The original dataset is maintained by the Cancer Genome Atlas Pan-Cancer Analysis Project. It is a random extraction of gene expressions of patients having different types of tumor, mainly 5 types of tumor, and there are 801 instances which are stored row-wise, and 20,531 attributes or features which are stored column-wise. The initial observation of data revealed that there are no missing values. The very first attribute is categorical. The data type of all other attribute is number. Here is a tree map showing the sample composition. BRCA stands for breast cancer, breast invasive carcinoma. KIRC stands for kidney renal clear cell carcinoma. LUAD is lung adenocarcinoma. PRAD prostate adenocarcinoma, and COAD colon adenocarcinoma. We can see that about 38% of the data is made up of breast cancer, and about 18.23% is kidney cancer, 17.6% is lung cancer, 16.98% is prostate cancer, and 9.74% colon cancer. Gene expression data are typically gathered as read counts. These read counts can vary greatly across genes and cell samples. There are two main approaches to normalize RNA-seq data for read counts. They are RPKM, which is reads per kilobase million, and FPKM, which is fragments per kilobase million. And there is a newer method of normalization that has been introduced, which is TPM, which stands for transcripts per million. Since all of our read counts in the dataset are whole numbers, this means that the data is normalized, but we do not have any information about the gene length or original read count, so we cannot really tell whether the data is normalized using RPKM or FPKM. The data set we acquired, as said, is already scaled and standardized and is very clean, and there is no missing values. This saves us tremendous amount of time not having to perform these functions, and we can focus on our analysis sooner. As part of the EDA, we performed a cluster analysis. We did hierarchical clustering on the full data set to find out if we can successfully identify 5 clusters, each one representing a unique cancer type. The data was transposed in order to perform the hierarchical clustering. Several methods such as average Euclidean distance, complete linkage, and single linkage were performed. The best dendrogram showing distinct cluster was obtained by using average Euclidean distance. Here shown is a dendrogram obtained by using average Euclidean distance, and we can see that each color represents one cancer type, and we can see that there are 5 clear clusters and probably one really small cluster of breast cancer, which might be worth exploring. Since our dataset has more than 20,000 features, dimension reduction will be key to our project. And principal component analysis was the first technique we used to reduce dimensionality of this dataset. And since like I said, there are over 20,000 gene features, and many has high correlations with each other. Removing or reducing this dimensionality will better serve our modeling techniques. So the first step toward reducing the dimensionality is to analyze a scree plot to identify the number of components that could be interpretable. Here, on the left, you see a scree plot showing the x-axis shows the principal components and the y-axis shows the amount of variance each explains. And we can see that up to 8 principal component is enough to explain most of the variance in the data. In order to justify the PCA analysis and choose only the first 8 components, a plot of cumulative variance explained by each component is analyzed, and you can see on the right you see the amount of a plot showing the amount of variance explained by each principal component, and we can see a sharp rise in the first few components, and about 7 or 8 it starts to flatten out. Therefore, it is safe to assume that the first 7 or 8 components are reasonable for interpretation. And the calculation also shows that the first 8 components explain more than 50% of the variation in over 20,000 genes. Using this information, genes were selected for further modeling by taking the top and bottom 10% for each of the 8 components based on the loading values. This approach let us shrunk the data set to about 8,000 genes compared to the original 20,000 plus genes. This new gene set was modeled using a bagging technique called random forest. We selected random forest because many machine learning methods perform very poorly on high dimensional data where high P and low N, which is our case, and random forest is a reasonable one for the data that is high P and low N, and it can also handle both high correlation and interactions amongst the other variables. So using random forest, we were able to identify important genes with a classification accuracy that is greater than 99%. The models were run under tenfold, three times repeated cross-validation. The initial result is very encouraging to see that we are able to identify different types of breast cancer and the important genes that are associated with them. Next, Dinesh is going to take over and explain the modeling part.
Thank you, Subha, for introduction to our data and highlighting the challenges of handling data when number of observations are much smaller than that of features. Hello everyone, my name is Dinesh Chaudhary. I will talk about models and their findings, that is, mining insights from the data. And this is a glimpse of what I am going to talk about. As Subha stated, we have 801 patients' gene expression data and 20,531 different genes. This data is associated with levels, cancer type, such as lung cancer, kidney cancer, etc. This is our target. Our modeling objectives are aligned with our business goals as described by Travis. The first objective is to detect the cancer type a given patient is suffering from. The second objective is to identify the set of most influential genes contributing to classify these cancer types. This slide shows how data and information flow through our subcomponents to produce the final goal. We receive our data from our research department. This is fed to our machine learning component. This component has two outputs: cancer classification prediction and the most influential genes. Cancer classification prediction information will then be passed to healthcare experts for validation and further investigation. The most influential genes data will be combined with other signals such as demographic data, healthcare parameters, etc., and will be passed to another subsystem called drug discovery. The output of both the drug discovery subsystem and experts analysis will then be passed to a subsystem to personalized cancer therapy system, and this system will be used for treating patients. Chauvin has rightly pointed that it is important to keep the cost low to compete. So to save development cost, we have used open source software such as Linux, R, Python, etc. We also use Quest cluster for computationally extensive tasks. Performance measure is critical. To measure the performance of our models, we chose F1 score. As Suva explained, we have imbalanced data. We have 38% cases of breast cancer, while less than 10% of colon cancer. F1 score is the weighted average of specificity and sensitivity. Therefore, it takes both false positive and false negative into account. So it is a good metric when data is imbalanced, as it strives to have a good balance between specificity and sensitivity. It punishes for extreme value as well. But the question arises, why not accuracy, specificity, or sensitivity? Accuracy is percentage of correct prediction, but it hides the underlying distribution of response values. It works well on balanced data, but misleads on imbalanced data. A low specificity indicates a large number of false positives, while a low sensitivity indicates a large number of false negatives. F1 score works in all situations, while others favor one condition or other. This is why we chose F1 score as a metric of performance measure. We need to keep aside a test dataset to see how our model performs on unseen data. Since we have imbalanced data, we split it into training and test set using stratified sampling to prevent sampling bias. This ensures that our test set is representative of the full data set. Most of the machine learning algorithms expect numerical features to be on the same scale for better performance. We use a standard scalar technique to scale. This minimizes the impact of outliers in the data. The transformed data has zero mean and unit variance. Since categorical levels are already provided, we use supervised learning classification approach for our modeling. We train the model with logistic regression and decision tree. Believing in wisdom of crowd, we tried several of decision tree based ensemble methods such as random forest, extra tree classifier, etc. For model training, we use tenfold cross validation to select the better performing models. All models perform really well. Based on F1 score, we shortlisted logistic regression, extra tree classifier, and random forest models. These three models yielded 100% F1 score on test set. This was very impressive. But to be aligned with our business objective, we need our models to be easy to interpret as well. Logistic regression provides this based on probability of each class, but we need to identify most influential features, that is the genes. These are provided by extra tree classifier and also by random forest models. Both are equally good. However, the team is more compatible with random forest model. Therefore, keeping the maintenance in mind, we chose random forest model as our final model. We recommend the random forest model as it is aligned with our business objective. At the same time, it performed extremely well on the test set. It is easy to interpret in terms of identifying important features. Also, it is very easy to maintain. On the left, we have a confusion matrix. This depicts the prediction on test data. The color diagonal represents the true positive of each class. All other numbers are 0. This means that there are no false positive or there are no false negative. Thus, for each class, our model predicted 100% correctly. The table on the right shows the top 6 most influential genes. As a next step, after approval, we will deploy the model in production. We will monitor the performance at a regular interval. Since the model degrades over time, we will train it with fresh data periodically. That is all I have for today. Now,
Thank you, Dinesh. Now that we understand our models, how do we take the information from those models and turn those insights into action? We decided to use Tableau as a software for visualizing our information and turning those into interactive dashboards and mobile applications. Tableau is the industry leader in business intelligence and information dashboard design. It's a software platform that provides the opportunity for a developer like me to take data and turn it into an end user application that is extremely interactive, provides a ton of customization, and is also really easy to use. This application requires the similar type of skill set that might be required for advanced Microsoft Excel or Access usage. The first part of this application that I want to demonstrate is the desktop version or the developer version. So this is where I created the entire app. And one of the reasons that we chose Tableau is because of the features that it has to allow you to view the same information, but to set it up in a way that you could have different layouts. So for a tablet or for a phone, the end user at the end of the day can still get what they need out of this information, regardless of which device that they're using. So that was one of the wonderful features of Tableau that we chose it for. Also, the ease of use in that just being able to drag and drop our components around, give it a different look and feel. You can see that it's really quite easy to completely change the experience and look with a drag and drop type approach. So now if we go look at the live version of this app, we can see first of all, our tree map. The tree map was already talked about by Suba and it was in our report, but now if you hover over it, you can see that we've provided information to the end user in these little pop-ups that tell them how to read this chart. It gives them some information about breast cancer, how many samples had breast cancer, what percentage of our overall data set it was. And you can see that it also has highlighted breast cancer across the other two visualizations on this view. So now we can also, it says that select cancer type to filter the other visualizations. So if I click on breast cancer, now suddenly both of my visualizations are really focused only on breast cancer. So we can now dig into breast cancer deeper. We can see, for instance, that this particular gene is highly expressed in breast cancer based on the coloring. And then if I want to look at that gene further, now I can look and I can see that sample 545 had an expression level of 11.77. And I can see here that sample 459 had an expression level of 14.06. So this allows us to go from a very high level understanding that there's 300 breast cancer samples out of the whole data set that uh, we're digging into here. And now we can get down to every single samples level on a particular gene. So we can dig into the type of information that we want at the level that is necessary to answer our questions. Now, if we go to the PCA detail tab, we can see so the PCA or principal component analysis was essential for us to understand how easily we would be able to discern cancer types based on gene expression alone. So we can see these clear groupings of our different colors, which stand for different cancer types. Now, this is, again, another great feature of Tableau. It allows you to apply a coloring schema and it will carry through from visualization to visualization. So these are all different visualizations with the same formatting, which is fantastic. But we saw that we had great separation, but we also discovered here that there's in this gray area where we've got a clumping of breast cancer cells that maybe look like they're slightly different than the rest. So we dug into that a little bit and we split those up into two groups. And so now you can see the second group is orange. And we can see that it's pretty well clustered around the various different visualizations. But some of these get a little messy. So now we can filter this down. We can just look at breast cancer to breast cancer and look at that. Now we can just see how much can we distinguish between the two breast cancer classes. So this really led us to believe that perhaps there's a different type of breast cancer that we've identified here by accident that is worth digging into and creating a more targeted therapy for, or creating two therapies, for instance, so that it would be more targeted and help the cancer patient more. Just to kind of note, this is a parameter that was programmed to switch between the two ways of viewing the information. And this is a filter that's based off of one of the attributes of our data, the class type or the cancer type. And now that I'm going to the next view, those are going to actually carry forward. So, which is also a great feature of Tableau is that you can synchronize the views so that whatever I select on one view carries over to the next, and I don't have to reselect those items to continue my discoveries. So here we can see, based again on our top 50 important genes from our model, we can compare breast cancer class to class, and we can see that, a lot of the same breast cancer, or the cells have a lot of the same genes are critically active and highly active in these two different classes. We can hover over them and see that this expression level is 1206 and this one is 1147. We can look at this one and see it's 1050 and this one is 1116. We can see that this one is 1254 and this one is 1322. And what we saw is, again, most of these genes are the same. You have highly active gene, highly active gene when you compare the two breast cancer types. So really what we wondered about is if we had additional demographic data, could we maybe understand that maybe this is a earlier stage of breast cancer? We don't really know that. We don't have that data to complement our analysis. So if we get some additional data, can we maybe say that this is a way for us to do an early prognosis because we can recognize these patterns happening in the earlier stages of cancer? Or, is there other demographic information that would have led us to a different conclusion? It would be perfectly explainable. It's perhaps true. So we can also look at the gene signatures for all of our cancer types. So now I'm going to lump breast cancer back together. We're going to look at our 5 original cancer types that we saw. And we can see in importance from left to right, our most important gene is here, very active in lung cancer. So we see a very high expression of this in lung cancer. We see very little of it in the other cancer types. So we know that this particular gene is incredibly important to lung cancer cells. And this indicates that it's easily discernible from the other groups. And perhaps, being this um, strongly indicative of it being lung cancer, maybe this makes it a target for one of our first projects. Maybe we develop lung cancer treatments first because it is clearly different than the rest. And we know to target, these genes that are incredibly active. You can see again, this gene is also very active, and the other cancer types it's not. Um, and then you can see, our fifth important classification gene is gene 203, and it's highly active in prostate cancer, and it's not very active in the other cancer types. So again, this creates a target for us. So when we develop prostate cancer treatments, we know that we need to focus in on these critically important genes that are really important to prostate cancer. So this helps us create these more targeted therapies. And another thing we can do is you may have noticed or may not have, that as I'm looking at this, it's also highlighting over in the right. There's that chart in the right is a little bit busy. And so having this highlighting kind of helps us discern the information out of it like a little bit easier. So we can see, hey, this was an important gene. It's very, yeah, there's some variability, but the variability is really quite relatively small when you compare it to relativity of other genes and other cancers. And so this makes us feel really confident that this gene is always active in prostate cancer because it is so different from all the rest of these. So this kind of information helps us to determine, again, which treatments to develop and which. So I just wanted to show what this looks like on the mobile phone really quickly. So you can see the first view that we talked about with the tree map and the gene expressions, both at cancer type level or at the actual sample level. We can still get the same information that we got before. We can click on breast cancer, for instance, see the information in the pop-up, and then we can also see that the charts below have been filtered by the breast cancer class. We can click on it again, it'll remove that filtering, and just like on the desktop. On the PCA detail, we actually did this one in landscape format. So Tableau offers the capability to create layouts for your phone that are either in portrait or landscape. So you can see in this one, we've got the landscape view of the PCA analysis. And then if we go to the gene signature, we can see all of that great information, the gene signatures for each cancer type and the volatility. Granted, this is a lot of information for a little tiny screen, but this is where those parameters to split the breast cancer into 2 classes and the filters come in handy. And now we're looking at just those 2 classes of breast cancer, and we can get a lot more information since we parse the information down. So we have all the same data and information and insights in the phone that we have on the desktop and all the interactivity. So let's just recap really quickly what we were able to do with our visualization tools and our mobile app. We were able to look at the composition of our data set and how many of each class, how many samples of each class we had. We were able to look at our cancer types and determine how separable they would be by gene expression. We were also able to describe and compare each cancer type's composition, which genes were active and which ones were not. And these were important inputs into understanding things like which treatment should we develop first and how should we develop or target our developments for these treatments by using the information of these genes. In addition, we happened upon the nuance in our breast cancer class, and that could be potentially a subclass or maybe even an opportunity for early detection. So now that we've had an opportunity to look at this application, Travis is going to wrap it all up with our final conclusions.
Thanks for a great demo, Carrie. So it's time to wrap up this work. After all the work that we did and the presentations that you've seen, it's time to review and wrap up what we learned, what we gained, and how we think we can move forward. At the beginning of this talk, during the presentation of the agenda, it was noted that the main points were also the objectives we set out. To revisit these objectives one last time and summarize, we were able to classify each patient's cancer type with very high accuracy. This gave us high confidence in our project and feel that we can move this forward. Because of this, we were also able to identify and rank the most important genes involved in each cancer, allowing for more targeted research efforts. We also identified a potential subclass of breast cancer, and this information could potentially be used to develop alternate products such as early detection kits or monitoring kits or protocols. And these weren't thought of before this work, but are a potential bonus outcome. And lastly, we created a user-friendly app and dashboard so the team members outside of our analytics group can do their own analysis and research and exploring for hypothesis generation, which is critically important to get multiple eyes on the problem and to allow the biology team or to give them a tool to better do their work and execute on their tasks. In the end, we ended up meeting all of our objectives. Our research and development team will be able to execute their strategy at a reduced cost because of this work. We accomplished this in many ways. Narrowing the number of gene targets was a key outcome. This massive reduction will allow the team to focus on the most important genes for each cancer type. These models are a solid foundation and stepping stone for future work that can be built upon, and the therapy testing that we do moving forward can now be better focused and prioritized. As a bonus, we potentially identified another product that we can explore and commercialize and develop further, that being an early detection kit or monitoring kit or something of that nature. Again, as stated before, this was not part of original scope, but a beneficial outcome after our thorough analysis and a positive result overall for SigmaFactor Pharmaceuticals.
This is not a video game. This is not a screensaver. This is the destruction of a cancer cell by the body's own immune system, thanks to medicine that didn't exist until now, and today can save your life.
We would like to thank the CEO for taking time to listen to this presentation and reading our report. Any further questions can be directed to me, Travis Walter, at the email address on the screen. If I cannot answer the question, I will most definitely forward on to the expert on the team that can. Again, we thank you very much.